Welcome to lesson 24 of Industrial Automation and Control. In the previous lesson we have got a basic introduction of CNC machines, which are widely used in manufacturing because of various advantages which we have seen. In this lesson we will take a slightly closer look at how the CNC machine actually creates the motion. As we have seen that for metal cutting, there has to be relative motion between the part which may be lying on a tool, on a table, or on in a chuck in a lathe, and the tool. Now in some cases, as we have seen, the tool undergoes rectilinear motion while the job undergoes circular motion, as in a lathe, while in the case of a milling the job undergoes rectilinear motion and the cutter rotates. So in this case, so we will see, basically we will see that how these motions are generated so that precise part dimensions can be created. So this lesson is on contour generation and motion control in CNC machines. Coming to instructional objectives, we will see the motion control requirements, the methods of interpolation for linear and circular trajectories. Sometimes there are parabolic trajectories also, we will not see that, and explain the open and closed loop motion control configurations which are used in the CNC machine. So basic elements of a CNC motion control system are as far as the control is concerned, it is the CNC what is called the axis controller, which is usually a microprocessor based board which interfaces with the electric drives. So they contain the variable voltage, variable frequency power supplies, usually power electronic, which interface to the motors, and these motors in turn interface mechanically through gears and lead screws and other mechanisms to the machine slide, the table, the spindle, etc. And typically we need to create two kinds of motion. One is spindle drive, where that is the rotational motion. Let us say for milling it is a cutter which rotates. So the spindle drive is on the cutter, and the feed drive or the table drive which is on the job in this case. The spindle drive problem is simpler in the sense that typically once the spindle speed is set, the problem is just to maintain the speed against loads. So it is a problem of speed control. The speed set point generally, once the material of the tool and the material of the job is fixed, it generally remains fixed. On the other hand, the feed drive or the table drive actually has to create XY directional, generally 2-dimensional, could be 3-dimensional also, motion. So that is the complicated part, and we'll look at that mainly, in fact almost solely. Typically there are two kinds of configurations which are used for smaller systems. Well, with less critical requirements we used open loop systems. So you have a drive, you have motors, this is the table that you can see. So so this is a table in which these are the two axes of motion, two axes x and y, which create independent motions along the two axes of the table. Now the point is that, as we have explained previously also, that the purpose of a control system is to achieve or make the output track the set point irrespective of disturbances. So that is the main job of the control. So the controller assumes a set point. So if you, in the context of the CNC, if you ask the controller that let the table slide move along the x axis at let us say 20 centimeter per minute, then the job of the controller is to maintain that, achieve that 20 centimeter per minute and then hold it. But what kind of motion is going to be created, what will be the velocity along the x axis and the y axis, these are the reference inputs to the control system, and they come from a different block called the interpolator. So, we are going to look at this interpolator in some detail today. So, these are the two things that we are going to look at. So, this is the control system and this is the interpolator. So, the interpolator tells the CNC drive as to where it wants to go, where it wants the table to go, and the control system achieves that. This is the way it works. And similar is the case for closed loop systems. The difference between an open loop and closed loop system is that you might have noticed that in the open loop system there is no feedback from the table motion. So, the interpolator kind of assumes that once it asks the table to move along a certain direction, it will move. So, typically, so that means that it has to be guaranteed, and which now to guarantee that you have to put certain kinds of restrictions on speed, etc., because if you try to move it too fast, then sometimes if you have a stepper motor drive, we will see when we study stepper motors that some pulses may be missed and things like that. So, this puts some restrictions, plus the whether we also need to ensure that the load does not become too much. So, these are used for smaller machines, because otherwise you might give a command to the motor, but the motor may not be able to execute it, and since you are not sensing it whether the motor has actually executed. So, you will be assuming that it has executed that motion command, and in which case your dimensions are going to be wrong. So, now in closed loop systems, as we are seeing that this is the actual motion. This is the actual motion that we want to create. In this case, we have only shown one axis. So, this is the motion sensing device or the encoder. Sometimes you may use a resolver. So, the encoder, from the encoder you get feedbacks, right. So, feedbacks are used to control used in the control system. This is the control system, this is the controller, this is the drive, and this is the motor, and this is the final mechanism which we want to move. So, these encoder feedbacks and these motor speed feedbacks, etc., are all used in the control system, and they are also used in the interpolator, because the overall cutting is actually a sequence of commands which the interpolator gives. So, the interpolator has to, in a feedback system, the interpolator has to know when its first set of command has been executed and it needs to issue new commands. Okay. So, there are lots of feedbacks, and these systems obviously do not make assumptions, and therefore they are generally more accurate, and they can work on higher loads. So, no, we'll first take a look at the, I think, yeah. So, you see that what kind of part dimensions we want to cut is actually specified in a part program by the engineer. So, as we have seen the structure of part programs. Part programs contains blocks, program blocks, in which there are various kinds of codes which specify that for a given set of operations, what are the parameters and what exactly needs to be done, what amount of feed, what kind of tool, which axis motions will take place, what kind of interpolations will happen, etc. So, we have, for example, there are some, it is written in terms of codes, and there are some codes called G codes which give information to the interpolator as to what kind of contour it is, whether it's suppose you have specified two endpoints, then the question is that whether the cutter will go in a will make a linear interpolation about these points and move like this, or will it make a circular interpolation? Now, if it makes a circular interpolation, then it also has to supply additional parameters, that where is the radius of this circle, because through these 2 points a large number of circles can be drawn. So once you provide these 2 endpoints, and you provide the coordinates of the center of the circle which it must follow, and then it will follow that circular interpolation. So these types of contour are provided, then these interpolations are going to be created in which axis or which planes, so that is selected. Various dimensioning conventions, whether they are absolute or relative, as we have seen in the earlier lesson, have to be provided. Feed rate controls have to be provided, that is at what rate it will move along that trajectory, but it will move at what velocity. So that cutting speed determines things like surface finish, etc. So that when it needs to accelerate, when it needs to decelerate, etc. Then there is something called cutter compensation, because you need to ensure that the motion is that the dimension is actually created on the surface of the part, but not at the center of the tool which is cutting. So there is some cutter compensation which has to be done, which we are not dealing with. Various coordinates have to be specified, and these are specified in what is known as a dimension word, and the feed word specifies these feed rates and their control. So at what feed rate? So such information, what I am trying to say is that these informations which are input to the interpolator are provided in the part program. Okay. So now let us see what the part program does with it. So based on the parameters of the part program, the interpolator produces velocity or incremental position reference. You see, there are, as we have seen, that there are 2 kinds of systems. One is a point to point system, another is a contouring system. So in a point to point system, while the motion is taking place, right, suppose you have a drilling machine. So when the drill is moving from here to here, it is not cutting. While in a contouring system, while the table moves, there is cutting. So for drills, the final position, 2 positions are actually important. That will decide where the hole is drilled, let us say on a plate. But from this point to this point, it can actually go along any track, and for saving time it generally takes the small straight line track and moves at the fastest possible speed, because it is not cutting at that time. While in a contouring system, suppose you want to, it is important to understand that suppose you want to go from this point, let me take a blue pen, suppose you want to go from this point to this point. So in a contouring system, whether you are going like this or whether we are going like this, it makes no difference, because it is the end points which are important. While in a point to point system it is not important, but in a contouring system it is very important, because you can see that the contour between these 2 points are in these cases are completely different. So the contouring system actually continuously along the trajectory, it has to maintain velocities, the right Vx and Vy values, so that the desired contour is actually generated, right. So so velocities or incremental position references for small parts of the overall segment are to be generated, and these are to be generated repeatedly and then send as references for each axis, that is x, y, z axis drives, to generate the desired contour. And we have to generate them, we have to compute them, recompute them repeatedly and so often that the contour error is left within a certain minimum, certain maximum rather. So this is the job of the interpolator. So with this, now how does the interpolator give command to the drive or the control system? So there are 2 systems. One is called a reference pulse system, where pulses are provided at certain frequencies to the motion controller, and each pulse indicates that a fixed displacement along that axis should be made. So small pulse, each pulse will make a small displacement, and these pulses are sent to the to the different axes, and the pulse frequency, at what frequency you are going to send it depends on the feed rate. So you are giving single bit, so the interface is a single bit which is either 1 or 0. On the other hand, you have a reference word system where you actually send the whole coordinate to the motion controller and say that either achieve this velocity or achieve this position in x and y. Okay. So in one case you are sending a number, multi-bit number, in another case you are sending a pulse, and the sort of the sum of the pulses which actually indicate the motion that you want to create. So let us first take the case of a linear interpolation, because that is the simplest, and see how a reference pulse linear interpolation can be done. So first of all, we have to understand that we are going to send pulses at discrete intervals. So if you want to create a straight line, then a straight line is nothing but an integration of a constant, right. So if we can send, if we can make an integrator and frequently add a word, add a constant number to it, then that integrator value will actually rise along a line. Now this integrator value can stand for the coordinate motion, right. Now, so while doing that, now only thing is that we don't want to send multi-bit numbers in the case of a reference pulse system. We want to send single bits. So how do we do that? So our simple strategy is that we keep on adding a fixed increment, and whenever this sum exceeds a certain number, then we send a command to the motion control system that now make this motion. So it is not that every time we are going to send a multi-bit number, but when the sum of these numbers, so we go on adding a number to an integrator, and when this increment becomes larger than a certain quantity, then we give one command to the machine that you now make one motion along this axis, right. So mathematically speaking, this is very simple, that we want to integrate a certain number p. We want to integrate a certain number p. So discrete approximation if we make, then we can write that z is sigma. So this is my previous value of z. I can say that this is zk minus 1. So I keep adding this pk into delta t to zk minus 1 to get zk. This is a standard rectangular integration. Now, so we compute like this. Now what we are going to add, that we can also change. In the case of linear interpolation, it need not be changed, and it can be, because every time we are adding the same constant p. But if you want to have some other kinds of interpolation, like if you want to have circular interpolation, or we want to have exponential interpolation, then we need to change this p. So we actually have this fixed length register q. I think we should see the picture first, and so you see this is the picture. So you see there is this q register which is finite, which is a fixed length register, pretty small length. So what we do is and this is my p register which gets added every time, and by using these two plus and minus inputs, I can increment the value of p, or I can decrement the value of p. In the case of linear interpolation, it need not be exercised, p is constant. So we keep adding this p every time a clock comes, we keep adding this p to q. So it will happen that there will be an overflow after some time, because q is a finite register, so we are adding a number to it. So after some time the number will be so large that it cannot be held in q. So at that point there will occur what is known as overflow. Now every time an overflow occurs, a pulse command actually goes to the drive system that now an overflow has occurred, so now move. And this overflow is actually, so when does overflow occurs? When suppose you have an n bit register, overflow occurs when the number becomes 2 to the power n. 0 to 2 to the power n minus 1, 0 to 2 to the power n minus 1, it can hold. The moment the number becomes 2 to the power n, there will be an overflow or more. So now we take this delta z out, and whatever is remaining after taking 2 to the power n out goes back to the Q register, and again p gets added to it. So every time there is an overflow in the addition, we send one motion reference pulse to the motion control system. This is the principle. So now we can look at, so what we are doing is every time we are getting to get zk, we are adding pk with the earlier value of the Q register, and then we are quantizing 2 to the power minus n into zk. So whenever zk becomes greater than 2 to the power n, this quantization result will produce a 1, right. So this 1 will now go as a reference pulse to the motion control system and will produce a motion, and what is now remaining in the Q register, this has been sent to the motion control system. So whatever is remaining from zk goes to qk, and again pk gets added. So this is the way it gets done, and you can easily see that the overall integral which gives zk is actually the sum of pi's, that is the true value of zk. But we are what are we actually sending to the control system? We are sending delta zi, but delta zi are actually related to delta pi, because this is nothing but this minus qk, because every time the rest of the value is stored in qk, so whatever is remaining is stored in qk. So actually this number which is being sent to the motion control system and this number which is the true integral can only differ by maximum by the length of qk, and so the difference is always bounded, and so as the real integral rises, this stepped integral delta z will also rise, and the error between the real integral and the stepped integral will never exceed a certain finite bound, right. So that is what is being ensured. So you see this is what is happening, that this is so I do not know why this is happening. So you see that this is the real integral and this is the sigma delta z, and it follows that, right. Okay. Now we are talking of two dimensional interpolation. So far we are talking of integrating along one axis. Now actually we have two axes. Suppose we have a table, we have to move the table in this plane, and the milling cutter, let us say, is rotating here. So as the part moves this way, that way, the cutter will cut and will cut the part. So we need to create two dimensional motion in this example. So how do you do two dimensional motion? So you actually have two such integrators, obviously. Now the thing is that they may have to be moved along different rates. Like for example, if you are moving along the 45 degree, imagine the xy coordinate. So if you are moving along this axis 45 degree, then the velocity along this axis and the velocity along this axis has to be maintained. On the other hand, if you are moving along this axis, then there has to be more velocity along y axis and less along x axis, right. They are related by the orientation of the line that you want to cut. So obviously, and the slope is determined by what? Determined by how frequently the delta z commands are given along that axis. So it depends on how frequently an overflow is going to occur. So now when will overflow occur frequently? When the number p which is being added will be larger. So if you add a high value of p, then it is possible that every time you add it there is going to be an overflow on an average. If you add a small number p, then it may happen that every 4 or 5 times you add p, you are going to get an overflow. So in this way, so by setting the value of p, the ratio of the velocities along the two axes can be controlled, and that is being shown here. So you have two integrators. So this is one p and this is the other p, right. So in one case you have p equal to a, and in the other case you have p equal to b, and you can find that the x and y coordinates will, so the slope is going to be decided as b by a, right. So the slope of the line that it will cut is going to be b by a. So this is the way. By the way, these integrators previously in the era of ordinary NC machines, these things used to be realized by hardware using a detailed electronic circuits, but now they are realized in software. So as far as these diagrams are concerned, they are actually like subroutine function blocks which get executed, and these clocks are not the hardware clocks which actually go to a hardware, but they can be like interrupts. So every time the interrupt comes, then these routines get recomputed and an output goes. So these diagrams has to be interpreted as like that. So you see that this is a case where we want to have, let us say, this b by a. So you see that to be able to generate, now you see that contour is important. So it is not that we can first give a amount of x pulses and then give b amount of y pulses, so even then the final position of the tool is going to go from a to b, but it must follow this path as closely as possible. That is contour generation, right. So you see what is happening is that in the first interval an x pulse is given but no y pulse is given. In the second interval a y pulse is given and no x pulse is given. Then two consecutive x pulses are given, a y pulse, an x pulse, and here both x and y pulses are given. So since both x and y pulses are given, so the table actually moves along this direction because both the motors are now rotating simultaneously. So this has to be determined. So this actually is determined by this, automatically gets determined by this overflow frequency. So whenever you get delta z for x, you get a x pulse. Whenever you get delta z for y, you get a y pulse, and they may occur simultaneously also. So you see this is a pattern by which this previous one was xy plot. This is an x and y versus time plots. So you can see that at various instants, for example, you can see that during this instant the x and y pulses are coming simultaneously. So this is the same thing. Now how do we control the, sometimes you need to control the feed rate. Why you need to control the feed rate? Because also because a table with a part on it, see sometimes you may like that, for example, let us say that the classic example is point to point systems. So you will like the motion to be created, that is you may like to move from point A to point B very, very fast. So you go up high speed and you give very fast feed rates, motion rates, but then when you approach the final point, then you slow down. Similarly, you may also do for contour making machines, because if you are cutting the contour at a very high feed rate, then as you are approaching the end point, if you don't slow down, then you are going to overshoot and you are going to spoil the part. So to avoid doing that, we need deceleration and acceleration mechanisms. So this is one way of doing that, where what we are doing is, you see, this is the clock, right? This is the clock. This is the clock and this is the clock. So the clock itself is being generated by an integrator, and so this is the feed rate. So this value of p sets the feed rate, and these are actually enable inputs. So when this is 1, then this pulse will feed, and when this is 1, this pulse will feed. When both of them are 0, these lines will be cut and the value of p will be maintained. So when you want to maintain constant velocity, simply set this to 0. So you will get these pulses at constant rate as clocks to this. When you want to decelerate, suppose, so you make this 1. So now what happens is that we can actually, by analysis we can show that this is like approximately, it will be like exponentially decaying the clock frequency. So what happens is that every time this goes 1, every time you get a 1 here, that 1 will now propagate here and it is connected to the negative input. So, the feed rate will now be decremented by 1. So, next time a pulse is going to be generated slower, again when another pulse is generated, again this is going to be decremented. So, as pulses are generated, if this input is 1, then the feed rate comes down and it can be shown that that will exponentially reduce the, so the pulse rate frequency will get will come down in this fashion over time. Okay. So, in this way one can control the feed rate. Now, we come to a circular interpolation case, and so what we see is that, so we want to what do we want to do? We want to move along this circle, right. So, suppose, so at some angle theta I we are in this position, and at after an angle delta theta I we want to be in this position. Now, what is one of the approaches is that you approximate the circle by a straight line, make this angle small. So, you actually are traversing very short straight line segments to make the circle, and if your segment is narrow enough, then you can almost achieve an arbitrary accuracy, very close accuracy. And in any case, remember that the accuracy of the machine cutting is actually limited to what is known as the basic length unit of the machine, that is the distance that it moves to get one encoder feed, one encoder pulse, let us say. So, smaller movements than that cannot be sensed and therefore cannot be distinguished between. So, therefore, there is a concept of a basic length unit, and we need to keep all, the aim is to keep the dimension errors limited to that. So, so this is what we are doing, successive coordinates. So, now we will see that if we did a linear approximation. So, suppose we are here slightly off from the circle and we are moving along this straight line to this point. So, then we are going to incur two errors. The error over the contour is actually maximum. There are the extrema, these are the radius errors, delta ri's and delta ri plus 1, and this is known as a chord height error which occurs in the middle. So, we need to keep these things in check, right. So, some elementary maths, simple trigonometry will tell you the following. These are some simple relations which hold. For example, this xi plus 1 equal to ri plus 1 into cos theta I plus 1, yi plus 1 equal to this. Suppose we assume that we do such an interpolation strategy such that ri is equal to ri plus 1, and it may be a little different from the real r that we want. And suppose we assume that these segments over which we are generating trajectories are moving by a constant angle delta theta, then we can easily show that this becomes a linear relation, that is xi plus 1 is given like this, where a is cos delta. This is just cos a plus cos b formula. So, and b is this, and this is my height error, radius error, ri minus r, and this is my chord height error, which is r minus ri cos delta theta by 2. If you see the triangle, it will be immediately clear. For example, right. So, now cos delta theta by 2 is written in terms of cos 2 theta cos theta formula. So, and a is cos delta theta. So, we have this formula, that cos delta theta by 2 is actually this part. Okay. So, now we can, now suppose we want to have such a, we want to know, for example, first of all, that if we want to restrict this delta r and delta h to one basic length unit, then what is the, obviously as if you make this delta theta smaller and smaller, then this linear approximation will approach the circle. So, how often do we need to recompute these lines commands and then give the corresponding command to the machine? This is the question that we are following, that we are trying to solve. So, because the smaller this angle is, the faster we need to recompute this, and well, it may give some, it's a computational burden on the machine. So we have, this is a standard formula that cos delta theta by 2 is r minus, this is simple geometry. Now if we assume delta theta to be small, then we can make such approximations that sin delta theta equal to delta theta and 1 by 1 minus delta theta, 1 by 1 minus x equal to 1 plus x and things like that. So if you do such approximations, this is easy to derive that this is your r plus 1 by r minus 1. So if you want to have now, so from there you can find that what should be delta theta such that the radius errors are limited to one basic length unit. So it turns out that it should be 4 by root r, and so how many times do you need to compute? Normally these arcs are provided as, maximum arcs are provided as quarter of circles. So if you have an arc of angle pi by 2, then the reference word generation frequency is pi by 8 into root r. So this tells you that how frequently you should generate the new reference words to be able to restrict errors within one basic length unit. Okay, so what have you seen? So we have roughly seen interpolation. There are various other strategies. We have seen how to generate linear interpolation by very simple integration. We have seen how to generate circular interpolation using linear interpolation. Seen that by frequent enough generation of lines we can keep errors in check. We have also seen how to control feed rates, right? So for many of the parts, these are, trajectories are formed in terms of circular and linear segments. So that's the way the interpolator gives commands to the control system. Now we are going to take a look at the control system itself. So again, coming back, we have two drive configurations, and right. So we have two drive configurations. One is open loop, so just pulses are coming to the drive system. These are typically applied to stepper motors, because in a stepper motor, if you give one pulse, then the motor will rotate by a fixed angle, which is its resolution, which depends on its number of poles, number of stacks, etc. But it moves from one stable position. You give it one pulse, it will move by a small angle and then becomes steady in another stable position. And if you give it another pulse, then it will move another time. Sometimes if you want to increase the velocity before it really comes to another stable position and stops, we give a pulse. So before it stops, it gets that pulse and then moves farther. But it is seen that if you give these pulses too fast, then some of these pulses will be missed by the motor. So the motor will not respond to them, as if that pulse is lost, right? So what we are, that is the first thing. Second thing is that whether the motor will move or not, that also depends on the load. Now stepper motors are typically designed for smaller torque ratings. So first thing is that they are useful for small machines. They have velocity restrictions and they need constant torque environments, right? Now now the torque on a machine is actually dependent on the feed rate, depth of cut, and the materials, etc. So therefore, typically these kinds of drives are typically used for point-to-point systems, because because in a point-to-point system, let's say when the drill is moving, it is not cutting. So the load is constant. It is also small, right? And another thing is that the trajectory is not important. Only the first and the final positions are important. So you can move it at a relatively slightly smaller rate, so that you ensure that if you give 5 pulses, then it will move 5 distances and it will not miss pulses. So it's suitable for small point-to-point systems with small and constant load torques, and it needs only final position control. There is no contour required because it's a because it's a point to point system, and main thing is that they are simple, they are cheap, electronics is simpler. You need deceleration circuits because you need to bring down the velocity, because otherwise, because of the inertia of the motor, it should not overshoot. So this is a typical circuit for a point. So you see that this is a reference word system. So we have the required position is actually given by the interpolator in terms of a digital word that gets stored in a down counter. Now this from this down counter it goes to a deceleration circuit, that is if deceleration is required. Actually, what does the down counter, you see what is happening is that through the, this is the pulse generator, right, which is giving the pulses finally to the motor, then the motor to the drive, and the drive is giving to the motor, and then this table is moving. Now there is no feedback, but this is an open loop system. So when it gives pulses to this, it also gives pulses to this, so the counter moves, so the counter counts down. So at any time the value held in the down counter indicates how far it is from the final system. When the down counter value will become 0, at that time it has reached at the final position. So this deceleration circuit is actually activated based on the value of the down counter. So if it is close enough to the final position, then this deceleration circuit will decelerate these pulse rates, so that the machine slows down and finally stops at the reference position, final reference position, and does not do an overshoot. The moment this down counter becomes 0, the terminal count event has occurred and it has reached. So therefore this pulse generator is nothing but an oscillator. So that keeps on generating pulses at the frequency which is controlled by deceleration circuit, but these pulses are enabled by the terminal count. So whenever this terminal count is reached, then this AND gate this is put to 0, and this AND gate output will be 0, and no further pulses will go, and the motor will stop. So this is the way it operates. Now if you have closed loop, contrasted to this, there is this closed loop drives, which we have already seen that there are various kinds of feedbacks. So let's take a look at closed loop systems. In closed loop systems, you can afford to drive the system at a higher speed, because you are sensing the whether actual motion has been made by the table, and you are decrementing your down counter using that value. So even if the motor misses one pulse, the down counter value is not going to be incremented, and therefore the right number of motion creating pulses will finally come to the motor. So you see the main difference here, this is absolutely similar. The main difference here is that the feedback is going through an encoder. So this down counter is going to count, its value is going to be decremented only if the motor rotates and the table actually moves. Previously it was every time a pulse is given to the motor, the counter was being decremented on the assumption that if a pulse is given to the motor, then the table will move. That assumption is not here. So this is the basic difference, otherwise they are same, and you can drive it a little bit faster and with a little bit higher loads, even if loads vary and there is some problem, so at least the counter will not be decremented. Now the other kinds, other than stepper motors, the other kinds of motors which are used are DC servo motors. Now AC servo motors are also used, but we are not going to look at, actually AC servo motors from a control point of view behave pretty much like DC servo motors. In fact, the whole of power electronics and machines research tries to do that. So if we look at DC servo loop, we will get pretty good idea about how this thing works. So here what we are doing is that we have a reference pulse system here, and we are driving a DC servo. So it's not a stepper motor case. So what we are doing is that this is the motor transfer function. It turns out, we can see that when we see DC motors, that it turns out that the speed, see, we are trying to control the speed. So basically in a motor, in a DC motor, if you change the armature voltage, then it will change the current, flux is constant, so therefore it will improve torque, so the motor will move, and there is generally speed feedback in such drives, etc., especially. So we try to control the speed. So so the speed transfer function and the speed will simply get integrated to give the position. In fact, the encoder frequency, the encoder every time it moves it will give a pulse. So if you measure the pulse frequencies, they are going to be proportional to the speeds. So the speed is given something like this. It is dependent on the control voltage, it is also dependent on the load torque, right. And if you neglect the mechanical time constant, then this is going to be the you will get a roughly a first order system. So what is happening here is that the reference pulses are coming into this up down counter. This is an up down counter. So every time a reference pulse comes, this counter is going to go up, and every time the motor moves, this is going to go to the this is the down terminal. So this counter is going to go down. So this counter actually senses the, in a sense, see the counter is integrating whenever it is getting this, and it is integrating, it is coming down whenever it is getting this. So actually this value of the counter actually indicates a position error. So based on that you are giving a control voltage and the loop is working. Inside the motor there is a speed feedback tachometer, we have assumed. So what kind of typical velocity profiles are going to get generated? See, initially the lot of reference pulses will come and the motor will slowly start, it has an inertia, it takes time to build velocity. So the counter value will go up. As the counter value goes up, then the torque will also go up and the velocity will start to rise. See, the velocity is increasing, there is positive acceleration. After some time, as the velocity rises, the encoder pulses also go up, and then so the on an average the counter gets incremented equal number of times as it is decremented, and therefore the counter value is maintained. So the velocity is maintained, and then towards the end what is going to happen is that as the position error will reduce, so the reference pulses will actually stop coming. Their frequency will be reduced. So now there will be more number of encoder pulses. So this error will, so the counter value will also come down, and then towards the end it will become 0, and at that time the motor will stop, right. So there is a natural deceleration in the process, along with the fact that you can also slow down the reference pulses using a deceleration circuit in the interpolator. So this is a typical velocity profile that may be followed. So you can see that the position error actually changes like this, that if you just integrate the velocity profile you will get this position error. It is shown discretely. So initially the required position is going up because reference pulses are coming. For some time the encoder pulses are coming slowly, so a position error builds up, that position error is maintained, and then finally that position error gets killed. So similarly, you can have a reference word system which is a very conventional control system, where you simply use simply give a position command. So it's a very conventional position feedback using this typical cascade control architecture. That is, there is a loop inside a loop. So there is a tacho feedback for speed control, and there is an actual feedback. So this is a very conventional control loop which is used, and remember that these control loop designs are actually very important, because the transient response of these drives are actually very important, especially when you are doing things like cutting corners. So when you are cutting corners, then you can see that suppose you are trying to cut a corner like this. So you are initially giving only y-axis commands, and then suddenly you are stopping the y-axis command, and then you are starting to give x-axis commands. So unless the transient response is good, then the trajectories are going to be, so depending on the transient response, the actual trajectory may be different from the corner that you really want. So the transient response is actually very important for these systems. So again, with that was only one loop shown, and with respect to that, so now you have two loops shown. So this is a table. This is your y-axis control loop, and this is your x-axis control loop. So you see the interpolator is giving reference words here, and the encoder is giving feedback, and rest of the control loop is just shown by this transfer function. And there is an enable. So whenever the interpolator can enable these pulses, when it actually disables it, then these inputs go to 0, and then only encoder pulses will be coming, and the counter values will go down, as we have discussed. So typically you have, so you can, this is an architecture for actually generating. So basically it's nothing but a composition of T2 axis drives, but we must remember that the contour error depends on XY channel. This is very important. So this is one of the reasons why NC machine controls are so expensive, is because that the channels have to be very carefully matched, because your interpolation will assume equal response characteristics on the x and y axis, and if they are not matched, then they are going to create contour errors. So firstly, these loops have to be very high gain, and secondly they have to be closely matched. So we are not going into the analysis of that. So we are coming, so in this lesson we have studied command generation by interpolation and reference pulse and reference word generation. We have seen how basic strategies for interpolation of linear and circular trajectories, and we have looked at two different types of control: open loop reference pulse controls and closed loop. Reference pulse controls are typically used in open loop. Closed loop reference pulse and reference word control systems. Before we close, we will look at some points to ponder. So let us say state one advantage and one disadvantage of the reference pulse method. Obviously Reference pulse methods will have they require less interfacing, only one line going into it. They can interface with things like stepper motors. On the other hand, the disadvantages are also obvious. We have seen that there is always some error, and so it follows the curve from one side. Then state one advantage and one disadvantage of reference word method. Reference word method is the basic thing, that is, in fact reference words methods are getting more and more popular than reference word method, reference pulse methods, because now hardware and ADCs and electronics and software are so easy to are becoming much more easier to program and to build. So reference words methods are actually conventional control systems where you give a number or a signal as a reference signal, and the rest of the loops are designed. And compare any 2 points related to motion control of PTP and contouring systems. So first thing is that PTP systems are working, generally motion takes place at no load, constant load, and while in contouring systems motion takes place while cutting, so load can be different, load can vary, and load is generally higher. And in PTP systems there is no need to control in velocities while it is travelling, because there is no contour generation, only final positions need to be controlled. While in contouring systems, while the drive is moving, the machine is cutting, so at every point velocities are important. So obviously contouring systems are much more complex, both interpolation and control. And stepper and servo motors, again stepper motors have resolution problems. They only move by certain steps. Their control circuits are simple, while servo motors have theoretically infinite resolution, and but their control circuits are complicated. So this gives you some idea of the way motion is generated in CNC machines. So thank you very much. Welcome to lesson 25 on flow control valves of the course on industrial automation. Flow control valves are very important. So, after learning the lesson, the student should be able to describe the importance of flow control valves. They are found everywhere in process industries. Learn the structure of major types of flow control valves. Learn about their flow characteristics, because that is very important in designing the applications. And finally, how to actuate these valves and how to affect their characteristics to achieve a certain characteristic of the process control loop. So, these are the topics that the student is expected to learn from this lesson. So, the first of all, let us have a look at the importance of flow control. Flow control is probably the most important control in a process control application, and as we shall see during our process control module, that flow control loops form a part of most type of control loops. For example, they are parts of flow loops where directly flow has to be controlled. Flow is the final objective of control. They are parts of temperature loops, because temperature is generally controlled by controlling flow of either a coolant or let us say steam for heating. Similarly, there are air to open valves where if the air supply fails, then the valve will close. So, one has to choose a particular actuation configuration to avert industrial accidents under various kinds of failures. So, that brings us to the end of this lecture. So, as a matter of review, we have typically seen globe valve, ball and butterfly valves. We have seen various kinds of valve flow characteristics, both static and dynamic, and we have seen how valves are actuated and controlled. There is one aspect which is treated in books which is called valve sizing, that is for a given application determining the size of the valve. We are not talking about that, because this is essentially a process design exercise and does not concern automation and control. So, to end, points to ponder: first is sketch the cross section of a globe valve and indicate 4 of its major parts. You should be able to do that. What is the difference between installed and inherent characteristics? This is extremely important, and why this occurs. What is the main advantage of a valve positioner? Why one puts it? And finally, mention one advantage of a solenoid actuator over a pneumatic actuator and one advantage of a pneumatic actuator over a solenoid actuator. So, that brings us to the end of the lecture. Thank you very much.